Now, back to the class now. We're talking about vectors and complex numbers. Vectors, we'll start with vector, but you understand that vectors has a twin called scalars. A quantity can either be vector or the quantity can be scalar. A vector quantity is a quantity that has both magnitude and direction. But a scalar quantity is that quantity that has only magnitude but no direction. If, for example, I am standing at a particular point, maybe I'm at this point, and there is a market here where I'm going to. The distance from where I'm standing to the market, if it's 20 kilometers, that distance is magnitude, is the size, the magnitude. So when you measure from this point to this point, calculating the size of the magnitude, that is a scalar quantity. That is why we tell you that distance is a scalar quantity. But by the time I measure this distance and I consider north-east direction with respect to maybe 37 degrees, I've added something to it now. No, not just 20 kilometers, but I'm telling you 20 kilometers, not 37 degrees east. That is now direction. So, scalar quantities we only consider magnitude. But when the direction is not considered, it's now a vector quantity. So basically our class today will concentrate on vector quantities, which examples of vector quantities have things like force. Force is a vector quantity. We have things like velocity. Velocity will be vector quantity. Well, those are quantities that have both magnitude and also have direction. Now, that is that. So let's go into vectors in details. But as far as vectors is concerned, there are some parameters that make the study of vector possible. First of all, you must understand something we call modulus. Modulus. The modulus is just the size of a vector. Modulus is just the size of a vector. The size of a vector is modulus. So when you want to calculate the size of a vector, you call it the modulus of the vector. The other thing we want to talk about in vector is, for example, if a person is moving at a distance of, maybe moving at a velocity of v1, and this is the direction of the vector. The direction of the vector is shown with an arrowhead, and the length we consider the length as the magnitude, while the arrowhead shows our direction, meaning a vector quantity, magnitude and direction. Now if I consider v1 as the direction of vector velocity v1, if I have to place another vector, I will have another vector which is going this way. Now you see that the tail of the second one, which is v2, is standing on the head of the initial one. But these two vectors, if you want to combine the two vectors together, they will be combined together with another vector. The name of that vector is called the resultant of the vector. The resultant also means the sum total of the two vectors. So when I have something like this, I'll have something like this. You see the tail, and this will be the head. So the head, the tail continue from here. The head and the tail continue from here. So this vector here is the resultant vector. I can call it V3, which is resultant vector. So the resultant vector here is the addition of V1 plus V2. And this arrow is V3. So that is how combining vector work. But what about a situation where you have a vector of this nature, maybe F1, that's for forces, another vector F2, another vector F3, another vector F4, and how many vectors are we having now? 1, 2, 3, 4. 4 vectors. Now, to combine the 4 of them, the last vector that you get that combines them together, that vector is called the resultant vector. So I can call it arrow, which is equals to F5, is the resultant vector. So you have vector V1, F1, F2, F3, F4. So the resultant of all the vectors. Okay, so therefore, what's the resultant of the vector now? Is F1 plus F2 plus F3 plus F4. And don't forget, this arrow is F5. That is the resultant of the vector. So basically, vector additions, vector resolution. But now let's consider what we call direct vector as far as computation of vector is concerned. Now, if you have something of this nature, it's possible for you to say, I have a vector, something like this at y-axis and x-axis. If I have these two vectors A and I have the one at B, if I have to combine these two vectors by vector C, therefore the resultant of this vector, which is C, is equals to square root of A square plus B square. Please take note of this. The resultant of a vector C is square root of A square plus B square. Now, these two vectors, vector 1, vector 2, vector 1, vector 1, vector 2. So vector 1, vector 2. So vector 1, vector 2. If you bring them together, what you get is the resultant. That resultant, which is the third vector, will give us the resultant. That resultant is. But the question is this: you may ask yourself, what's the difference between? You do hear sometimes you hear something called equilibrant, resultant. Equilibrant is different from resultant. Resultants are used for vectors, but equilibrants are used for equilibrium. Equilibrant is just that force that keeps other forces in equilibrium. You have a house, everybody is quiet. There's a person that comes into the house, everybody will be happy. That person is the equilibrant of happiness in that house. So equilibrant brings about, keeps other bodies in equilibrium. It's that last thing that comes in, that fits in for equilibrium to be achieved. But resultant is just the sum total. But sometimes equilibrants can act as resultant. So that's the difference. Now, from here, you have C is square root of A squared plus B squared. That is that. So automatically, the modulus of this, the modulus of this resultant is equal to the size of. Let's consider vector in componental values. Maybe you are having 10 Newton, you are having 3 Newton. The resultant of this is equals to square root of 10 squared plus 3 squared, which is equals to square root of 100 plus 9. That is square root of 109. So that's the resultant. But what about a situation where you consider a vector, which is a different, okay, this one is called resolution. Let's talk about resolution of vector. Now, if you want to resolve a vector, it's a different thing entirely. That's the y-axis, and this is the x-axis. If you have the y-axis, probably starting at point O, which is the origin. Every graph has an origin. The origin of a graph is the point O. So, at the point O, if you have a problem of this nature, maybe at point O you are having somebody taking out a value. It's starting from here. Maybe it's resolved. As it's resolved, you have your values being taken out. It's resolved. So from here, you have angle theta here. Good. Now, from that angle theta, and the value that is here is the value u. The value is u. But we'll now use a theorem called the Lami's theorem. The Lami's theorem is simple. Lami's talked about the direction or where the angle is. Wherever the angle is according to Lami's, that value there will be cos. So if you look at this, on this axis, on this y-axis, the value of u on the y-axis, that's horizontally, you have something of this. The component of that value there will become, that's uy, and that value become u cos theta. But vertically, it will be, this is x. Uy will become u sine theta. So always remember, wherever the angle is cos. Where there is no angle, it's sine. So that's what we call resolution. Whenever you are resolving a vector, remember, where the angle is cos, where there is no angle, sine. What it means is that if I consider a problem of this nature, I used to say if I consider a problem of this nature, what it gives to me, invariance, is that if I have a problem like this, I have 10 Newton. If I have 10 Newton and I have at 30 degree, what it means is that for u on the y-axis, what I will get on the y-axis is 10 sine 30 degree. And on the x-axis, what I will get is 10 cos 30 degree. So I'll have 10 sine 30 degree, and here I will have 10 cos 30 degree. So because of that, the resultant of this vector will become square root of 10 sine 30 degrees squared plus 10 cos 30 degree squared. The reason is because, you should remember, the reason is because the resultant is x squared plus y squared. Beautiful. So now, whatever you calculate and get as value here becomes the modulus or the total resultant of that vector. Now, we've considered that. So we'll continue from vectors. Now, let's talk about components of vector, of unit vector. Components of unit vectors, it's as simple as the direct vectors we talked about initially. You discover that if these two vectors combine together, the resultant is arrow. For the resultant of arrow of this vector, the direction of this resultant is OR, from the origin to the OQ down to the value of Q. So OQ will give us A on the direction OX and B on the direction OY. This is OY, still the same thing, equivalent to this. So A on this direction is equals to AI. The I itself is the representation of a unit vector. The I dot stands for that unit vector. And the J, B is equal to also for the unit vector. So arrow is equal to AI plus BI. So the magnitude, which is the modulus of the vector, is A squared plus B squared. So from here, we'll discover that OQ will give us the vector direction divided by the modulus. Now I said the unit vector, the direction cosine of the unit vector is given. These are the direction cosine. But direction cosine can also be cos as x over root of A squared plus B squared, because the modulus of arrow is this value. And it can also be cos beta to be equal to cos beta is also the same thing as y over root of a squared plus b squared. So these are the direction cosine of the vector. But now we have an example which makes it simple and easy for us to digest the facts behind unit vectors. So find the magnitude of the following. Now the magnitude of this, we'll consider the first question. It said question A, which is 4i plus 3j. That is for, so we should consider, it said find the magnitude. So the magnitude, I told you, is also called the modulus of the vector. Now, what's the magnitude? The magnitude is of the modulus of the vector. Find the magnitude. The magnitude will give us square root of, before you do that, the 4i is self. This value here is x, and this value here is y. If you continue, it can become z, w, and co. But for this is x and y. So the magnitude now will become square root of x squared plus y squared. So that will give us square root of 4 squared plus 3 squared. So 4 squared, 3 squared will be, 4 is 16, and that's 9. That will give us 25, which is 5, possibly 5. Good. Now for the second, which is B, it gives us 6i plus minus 7. So that will give us square root of 6 squared plus minus 7 squared. Please don't forget, when that minus and the square operates together, it becomes positive. So from here we have square root of 36 plus 49. So that gives us 36, 49 will give us 50. 50 plus 35, that will be 85. Everything else will be 85. Good. So now that is that. So finally, I can take the last question too. The last question is in 3 tiers. The last question, which is question C, it says 2i. Just finding the magnitude. The magnitude is also called the modulus, the size, the modulus. So you can see modulus, modulus. So from here, you have 2i plus 3ji minus 5k. So you see this is in 3 tiers. So because it's in 3 tiers, it's not difficult. You just take that 2 squared, that's y, x, y, z. Now it's not x, y, z. So the k stands for the z. So you have 3 squared minus 5 squared. So that will give us square root of 4 plus 9 plus 25. 4 plus 9, 25. 4 plus 9, 25. This will be 13. 13 plus 25 will be 8. And that will be 3. 38. So that's that. So when you are asked to calculate the value of the modulus, it makes it easy. For example, you have this now, you understand this. For example, you are asked to add these vectors for me. If I'm asked to add this vector, maybe I have another example. I'm asked to add the following vectors. If I'm asked to add the following vectors, they are unit vectors. Maybe I have this to be, 4. Maybe 4i plus 2j. That's one vector. The second vector is minus I plus 3j. And the third vector is 6i plus j. If you are asked to add this vector, how do you add them? By addition, you just add all of them. 4i plus 2j minus I plus 3j plus 6i plus j. You're adding everything together. So when you add, what do you get? 4i minus I, that's 3I. 3I plus 6I, that would be 9I. 2j plus 2j plus 3j, that's 5j. 5j plus 1, that would be 6j. So that would be 6j. So if, for example, you are now asked to find the size of this, for you to find the size, what do? That becomes square root of 9 squared plus 6 squared. So 9 squared, 6 squared. What would that become? 9 squared, 6 squared is 9 squared, 6 squared, that's 81 plus 36. So 81, 36 surely will be 7. That will be 7, and that will be 12. So something like that. So with this, it's easy. So you just add them. If you're not asked to find the size, don't forget the meaning of the size. The size also means the magnitude of the vector. Now, from there, I can consider something of this nature. What about I'm asked to find the unit of this. Maybe I'm asked to find the unit vector of something of this nature. Maybe I'm asked to do this. Find the modulus of 4,3. I'm asked to find the modulus of 4,3. What does this mean? 4,3 means modulus of 4,3 is equals to square root of 4 squared plus 3 squared. Now listen, that will become square root of 25, which is 5. Now, this value here, 4,3, also means 4i plus 3j is what it means. But in a situation where you are told is 5 minus 8, it stands for 5i minus 8j. Please take note of that. So this is how it works. So from there, we'll move to the next stage now and consider more theorems and questions in vector analysis. Now to round this up, we need to consider something else that has to do with directional vectors. I'll take that from one of your question book, question 4. He said, find the unit vector in the direction of the vectors. Find the unit vector in the direction of the vectors, of the following vector. Good. Now, it's easy. If you remember, the unit vector has a direct formula. Why I told you OQ, if you take note of that, for that direction is the same value as AI, or let me use X plus YJ divided by X squared plus Y squared. And please don't forget, this is a module. Now, if I want to consider question A, it's simple. What I just need to do is that question 1, A is equal to 4i plus 3j. Simple. First, let's find the modulus of this. What's the modulus? The modulus of this is equal to square root of 4 squared plus 3 squared. And surely that's square root of 25, and that is 5. So therefore, the directional cosine of A, that's the sign for it, you put it at the top. The directional cosine for this will become 4i plus 3j divided by 5. Sometimes, if you want to make mathematics interesting, you can make it 1 over 5 into bracket 4i plus 3j. Depends on you. Now, that is for question 1. Now, for question 2, which is B, it's simple for us to analyze that. Now, what do? You can tell yourself that B is equal to 3i plus 7j. Now, what is the module of B? The modulus of B is square root of 3 squared plus 7 squared. And I believe that will give us square root of 9 plus 49. And I believe 18 plus 40, that surely will be 58. So therefore, B direction will become 3I plus 7J divided by root of 58. That's simple enough. So the last one, but not the least, is C. It's a third question. So C is 5I plus 3J, and the module of that will be square root of 5 squared plus 3 squared, and that is 25 plus 9. 25 plus 9. Simple. So you take the modulus first. After taking the modulus, you end it up by saying this will give us square root of 34. So therefore, the module direction of this, you can see the sign on top, the direction of that will give us, what is the value there? 5I plus 3J divided by root of 34. So, simple. So with this alone, it's simple, it makes it easy. So you cannot make mistakes. All you need to do is take a value, take a module, place the value at the top, and the module beneath. Numerator, denominator. So with that, we've rounded up what we call vectors. Now we have to consider the next one called complex numbers. Now, in continuation, now that we've considered vectors, let's consider the complex numbers. Complex numbers. An interesting topic as far as mathematics is concerned. Now, sometimes the word complex, meaning it's a value that tends to be abnormal. It's an anomalous value. So we say it's complex. Now, take a look at it. When you solve your mathematical induction, if you tap your calculator as you're sitting watching this class now, you observe something. If I take this value out, for example, I say see square root of 4, what you get in manipulations of number is 2. You agree with that? But if I say square root of 2, I should have 1.414 or something of that nature. But in the course of manipulation of computation of numbers, if I write this value, square root of -2, press this in your calculator. Tap that in your calculator watching this class. If you tap this, your calculator will tell you error. The reason is that I will tell you syntax error. The reason why it will tell you error is because this is a complex number. Now, but that does not mean you cannot calculate complex numbers on your calculating machine. But there are code values for doing that. Now, this is an error. So if you have -7, it will also tell you error. Error. It will tell you error. If you have root of -1, it will tell you error. Error. Error, error. Syntax error, syntax error, syntax error. So it becomes syntax error all through. But as far as this minus sign is there. But today, I'll tell you in this class that this value, which you call, or your calculating system call syntax error, you can manipulate them. Now, these numbers, if I have -4, for example, do something here. I can just tell myself, good. This value here can also be root of -1 times 4. I believe you understand that. It can also be this. Because -1 times 4 will still give us the same value. It can also be something of this nature. Maybe you change your mind as, okay, let's make it root -1 times root 4. It will still give you this because of the basic principles of solid. But this thing is still a problem. still a problem, it's still constituting a nuisance. So because it's a problem, what you just do is that you have to represent it with something else. What do you represent it with? Let your value, let's your value j squared be equals to root of minus 1. So if I have these two values, I can say j squared is equals to minus 1. So when values have minus in the square root, you basically refer them in this state as complex numbers. So from all these values down to the next values, it becomes easy for us to look at it. J squared is equals to square root of minus 1. No. The reason is because j squared equals to square root of minus 1. It's not real. But I can say that j itself can be equals to root of minus 1. This is possible because this is not real. It's not real. And I don't like things that are not real. So j is equals to square root of minus 1. Okay, if j is square root of minus 1, so wherever I see that root of minus 1, I can represent it with j. So because of that, if I write now that this value here is square root of minus 4, I can call it root of minus 4 times, I can call it root of minus 1 times 4, which becomes root of minus 1 times root of 4. And that becomes root of minus 1 is now represented by j. So if it's represented by j, I'll call j times 2. That becomes 2. I can call it or 2j. Depends on what I want to do. So in recent value, I can write j2 as value. Now, what about if I have something like minus 9? That becomes root minus 1 times root 9. And I believe that will give me j3. So this particular value, j, is the notation of a complex number. So you can always remember that it's the notation of a complex number. Now, that is that. So we can take out rows and deductivity as far as complex numbers are concerned. But the first one we're going to consider, class, is that we're going to consider the fact that these complex numbers, they can be added and they can be subtracted. But before we start talking about the additions and subtraction of this complex number, let's talk about something called the powers of this complex number. Let's see the powers. It has powers of this complex number. These powers can be of different type. Powers of this powers. Powers can be analyzed in different form. In theology, they say powers. In the psychology, you talk powers. But now we're talking powers mathematically. Good. So powers, I believe very well you can say, you remember that minus 1 is equal to j. That's j. Remember that. We just discussed that now. But do you know that this is a square root? If the square root crosses the equality sign, it becomes a square. So because of that, that is minus 1 is the same thing as j squared. Same thing. Same. It's the difference. So if you find the value of minus 1, it can be represented as j squared. So j squared can represent minus 1. Take note of that. So because of that, This is the first notation. This is my first notation. So this one should be inside a box because it was analytical. This is my first notation. So what about a situation where I find J3, J cube? If I find J cube, how do I analyze J cube? J cube will become, J cube can be J into bracket squared. That can be J. The reason is because it can be, or I can make it J squared and J. Because J squared times J outside is the same thing as J cube. But the J squared itself is what? The J squared itself is minus 1. So it becomes minus 1 J, which is equals to minus J. So anywhere you see J cube, it can be represented by minus J. Let's try J4. J4, 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 oh, it's a car's name, J4. J4 is squared, squared, that's J4. Because 2 times 2 will give us 4. So that's J4. So J4, 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 J4. So J squared is minus 1. So you have minus 1 squared. And that gives me, oh, minus 1 times minus 1, that will be 1. I'm done with J4. So let's try J5. Another power is coming up, J5. So J5 is J raised to power 3, J raised to power 3 into bracket J squared. If you multiply these two together, it will give us J5. Because 3 plus 2 is 5. So from here, I can take something like this out. What is J3 again? Oh, J3 is minus J. Oh, J squared, J squared. J squared is minus 1 times minus 1. That's J squared. So if you multiply these two together, what do you get? Minus times minus plus, that becomes J. Can we try 6? Let's try the guy J6. J6, the power J6. Let's try the power J6. The power J6 will automatically give me J squared raised to power 3. Because 3 times 2 will be 6. It's a different thing from J raised to power 3 into bracket J raised to power 2. They are two different things. Here you add the power, but here you multiply. There's no J outside. So 3 times 2. So from here, what do I get? I will get J squared. J squared, that's J squared. Oh, J squared is minus 1. So it's minus 1 raised to power 3. So minus 1 raised to power 3. Minus 1 times minus 1 is plus 1. Times another minus 1, that becomes minus 1. So remember, J6 is minus 1. That is the manipulation of power. So you can take your powers from beginning to the end. The only thing you need to know is that minus 1 is J squared. That is the foundation of it. Now we're done with that. We want to analyze something else, which we call addition and subtraction of this complex thing called complex numbers. Okay, good. From there, we'll take the analysis further. Addition and subtraction of complex numbers. Complex numbers. Let's try that. Of complex numbers. Yeah, let's see the complex numbers analysis. Now, from complex numbers, we observe that if, for example, you have something like this, maybe you are giving 4 plus J2 is equal to maybe A, 3 minus J4 equals to B, and 1 minus J to be equals to C. And they ask you now, find A plus B as figure 1. Figure 2, you are asked to find A minus B. And figure 3, you are asked to find A plus C. And figure 4, you have to find C plus B. Probably you have something like this. It's simple. You can just take it out. Now we settle our addition and our subtraction of complex numbers. Yeah. You can see that the name complex number is just a buzzer. A buzzer in the sense that it's actually not complex number. What's complex about this analysis? Actually nothing. So from here you have what? A plus B. That gives me 4j to A. This. So what is the 4? What's the A? The A value will be 4 plus J2. Okay, let me use a bracket plus because of the Bodman's guy. So what's the other guy again? 3 minus J4. And because of that, let's now do this. If you look at that carefully, you observe that you can open the bracket now. 4 plus J2. But it depends on how strong your math is. You may decide not to use the bracket for addition and subtraction. You just take it directly. So from there you have what? 4, 3 is 7. Oh, J. 2J2 minus, that will become minus J2. Because 2 minus 4 is minus 2. So we have 3. And question 2. Question 2 is A minus B. For the A minus B, you have, where is it again? 4 plus J2 minus 3 minus J2, J4. So that will give us 4 minus 3 for this. Then we have plus J2 plus J2. Okay, let's even open this to the bracket first. 4 plus J2, to make it simple, minus times this will be minus 3 plus J4. Use minus to open the bracket. So what do we have? 4 minus 3. That will be 1. Plus J2 plus J4. That will be plus J6. So now, you can see it's different. For the addition, you have this for multiplication. So I've taken these and I've taken this. So it will be easy for you to just tell yourself, oh, I've taken first and second. So you can manage 1 and 2 for yourself. Enjoy it. It's sweet. It's interesting for addition and subtraction of complex number. So from there, we'll move now to multiplication, conjugates. From there, division is simple. So by the complex numbers for multiplication, complex numbers. So complex numbers can be multiplied. So for the multiplication of complex numbers, you can consider the fact that your normal multiplication is multiplying one value with another. 2 times 3 is equals to 6. If you are having something of this nature, for example, let's take this on bisective values. If, for example, you have x plus y times x plus, probably you're having 2 plus 3. If you want to multiply it, what do? You say x times 2, that's 2x. X times 3, 3x. Y times 2, 2y. And y times 3, that's 3y. So automatically that gives us 5x plus 5y. That is your normal multiplication. Now, if it is complex number, it's simple. If you are asked to multiply 3 plus J2 and maybe you are having 4 minus J2. Now what do you have? You're having these two. So solution to this is simple. 3 plus j2 into bracket 4 minus j2. There are two ways of doing that. Either you distribute them or you multiply them directly like this. Let's multiply them directly. 3 times 4, 12. 3 times 2j. That will give us, or you decide, if you decide to distribute them, it's simple. Then you have 3 this, that will be 3 times 3, that will be minus 6 j6. Let me write that very well. Minus j6. In the sense that 3 times 4, 12. 3 times j2, 2 times the 3, that will give us 6. And the minus sign in the front, plus times minus is minus. So from here, 4 times j2. So that will give us, 4 times j2 will give us plus j8. And the last one is j2 times j2. That will give us minus j square 4. Because the j times the j will give us square. 2 times 2 will give us 4. Now it's simple enough to say that from here we can take out values and say, okay, good. We have 12 minus 6 plus minus 8. That will become plus j2. But out here is a different case entirely. J square 4. This j square. If you remember from powers, the powers that we consider, if you look at those powers, you remember that for powers, j squared, that word j squared gave us minus 1. So wherever you see j squared, it's also the same value as minus 1. So that will give us 12 plus j2 minus 1, 4. That will give us 12 plus j squared. Minus times minus is plus. So that will become plus 4. 1 times 4 is 4. So if you add these two together automatically, that will give us 4 plus 12. That will give us 16 plus j2. So that's that. But what about a consideration where you are giving something like 6 minus j3? If you have to multiply it with 1 minus j5. So you have 6 minus j3 multiplied by 1 minus j5. Let's do that now. If you multiply them, 6 times 1, that will be 6. 6 times minus that will be j30 minus j3 times 1. That is minus, that will be minus j3. Minus j3, that will be plus j squared. 3 times 5, that's 15. So from here we can take it. Don't forget, j squared is minus 1 from our power analysis. So from here you have 6 minus j30 j3, that's minus j33, because minus 30 minus 3 is minus 33. So from here we're having plus j squared is minus 1, then you have 15. Minus 1 times 15, that's minus 15. So that will give us 6 minus j33 plus minus 1, that become minus 15. So 6 minus 15, automatically that will give us minus 9 minus j33. So that is the value. So that's multiplication as far as complex numbers are concerned. But we can shift that value out in the sense that under normal circumstances, I can consider something else for these values. Now, what is that I can consider as far as these values are concerned? I can consider something called the conjugate. There's something else called the conjugate of a complex number. The conjugate of a complex number. The conjugate of a complex number. So for conjugate of complex number, now we're going to consider, it's simple. Conjugate of complex numbers is the number values for conjugate. Like when you talk about the conjugate of sort, and conjugate does deal with the difference of two squared. Now look at it. If, for example, let's look at this theorem from De Morgan. Difference. Let's see the difference of two squared. Okay, don't bother about that. Recall this. It's called the difference of two squared principle. Recall that anytime you have a squared, let me say a squared, let me say a plus b into bracket a minus b. If you have this, that's De Morgan's rule. De Morgan said that this can become a squared minus b squared. So always remember this. So if you have value like, if you have a value like x plus y, x minus y automatically becomes x squared minus y squared. So if I have a value that is 6 plus 2 into bracket 6 minus 2, it gives me 6 squared minus 2 squared. And 6 squared is 36 minus 4, which will give me 32. So with this, it's simple. Because if you do the same thing out here, 6 plus 2 is 8. 6 minus, if you multiply them, it will still give you the same value as that. So now, from there, it's simple to say that with this same conjugate of complex numbers, I can say, find the conjugate of 2 minus 3 4 2 plus j3. If you find the conjugate of this is a solution to that. Very simple. Solution to that will give us 2 minus j3, 2 plus j3. So if you look at it, it's just the same thing as the difference of two squared principle. So when you take that, what would that be? 2 squared, and the other one will be minus j3 squared. So from here, 2 squared is 4. 3 squared, normally, under number 3 squared is 9. But j squared, that's j squared and 9. 3, 9. J squared. So, but don't forget what j squared is, class. What is j squared? J squared is minus 1, 9. So minus times minus will give us plus. Minus minus plus. So j squared 9. Now, minus minus being plus, okay, that becomes 4 plus 9, which automatically is equals to 13. So it makes it a little bit simple and very easy. So always remember, difference of 2 squared down, it gives you conjugate. So when it's minus, it's plus, they are the same values, but it's just that one is minus, one is plus. Just the way you have the difference of 2 squared, plus minus. Plus can come before minus or minus come, it depends. And that's De Morgan's rule. By the difference of 2 squared. Now, that's that. Let's consider something else called the division of complex numbers. Complex numbers actually can be divided. They can be divided. You can divide complex numbers. So those numbers that can be divided, that's division of complex numbers. Division of complex numbers. Complex numbers can be divided in the sense that when dividing complex numbers, it's simple. All you just need is to remember how to do what we call the rationalization of sets. Now, we can rationalize in this view. Let's take a look at this. If, for example, you are asked to rationalize values of this form, maybe you'll say divide. Maybe divide 6 minus J3 by 2 minus J2. Let's try this. What you just need to do for solution to that is 6 minus J3 divided by 2 minus J3. You divide it. They say you should divide, so you divide. 6 minus J3 divided by 2 minus J2. You divide, normal division. Now, when you do that, the first thing you are going to do is to what? Rationalize. You rationalize. When you rationalize, rationalization means that you multiply the numerator and the denominator by the denominator. Compatible theorems. So, multiply the num and the dim by the dim. Multiply the num and the dim by the dim. The numerator and the denominator by the denominator. So from here, what do you get? You have 2 plus J3. It's minus. It now becomes what? Plus. I'm multiplying the top and the bottom by the bottom. The top and the bottom by the bottom. But the sign will change. The top and the bottom by the bottom. But the sign will change. So what do I get here? I have 2 plus J3. So if I multiply this whole thing, it now becomes your direct multiplication of. So if you multiply the top, you have 6 minus J3 bracket, and I have 2 plus J3 divided. So here you have 2 minus J3 into bracket 2 plus J3. So now you discover that you have something down here which is a conjugate. Don't forget that. So that is the reason why your knowledge of conjugate is needed and necessary, because you need to apply it in polars and division. Now, from here, it's simple. We can just do a normal multiplication. 6 times 2, that's 12. 6 times this, that's, what do you got that? That's plus, that's J18, minus J3 times 2, that's my minus J6, that's J6, minus this, that will become minus J square, this J square, not J2, it's J square now. 3 times 3, that will be 9. So, divided, and this will be 2 squared, because it's a conjugate, down is a conjugate, minus J3 squared. So we are still there now, we are progressing. So with this, we can have 12. 18 minus 6 surely will be 12. So I will have 12, 18 minus 6 plus J12. But the question is, this guy is J squared, and J squared is minus 1. So I will have minus 1, 9 divided. Out here, I'll have this as 4. But this guy here is J3. So I will have minus this J3. The J will go for squared. That will be J squared. The 3 will go for squared. That will be 9. There are 2 things. So from here, I can boldly say that it's settled. I will tell you that 12 plus J12, this nonsense here becomes minus 1, 9. That becomes plus 9. This side divided. Out here, what do I have out there? This is J, so that will give me 4 minus 1, which is J squared 9. So that will give me 12. 12 plus 9. 12 plus 9 will be 21. So that will be 21 plus J2 divided by plus times minus, minus is plus. 4 plus 9, that will be 13. So therefore, the division is 1 over 13 into bracket 21 plus J2. So that's division of complex number. Very simple. So always remember, immediately you are giving division, What do? You rationalize the division. Does that mean? Multiply the numerator and the denominator by the denominator. And after doing that, you express your complex values. Express your complex value, you multiply the top, you take the conjugate of down, you express it down. And what do you get? You get that. Don't forget, j squared is different from j2. J squared is minus 1. Good. Now, we've talked about that. And that's simple enough to understand as division. Let's talk about the polar value. The polar value in that form. But not polar value per se, but let's talk about it as modulus of complex number. Please don't forget the name, modulus from vector. Modulus actually means the size. That size of it. That's the modulus. Now, let's go from there. Modulus of a complex number. Modulus of a complex number. A modulus of a complex number in analysis. It's simple. You can just tell yourself modulus value. It's still the same thing. But don't forget this. The modulus of a complex number. For example, a complex number is given as a plus jb. The modulus of this is simple. The modulus is given as square root of a squared plus b squared. So if you have an example like this, if you're having a modulus of 2 plus j6, what will that be the modulus? The modulus will be square root of 2 squared plus 6 squared, which is square root of 4 plus 36, which is equals to root of 40. So if you have a complex number of, maybe you're giving a question like this, 1 minus j7, what would that be? 1 minus j7, what would be the modulus? The modulus would be square root of 1 squared plus minus 7 squared. So that gives me automatically, what would that become? If you take that out, that becomes something of square root of 1 plus 49. That's square root of 50. So always remember, the modulus of a complex number can be calculated as its size, just in direct form. So, we've analyzed this and we've come to the end of complex number analysis. I know you enjoyed the class. I'm still your instructor. We'll meet in other classes. Thank you.